Let's look at a graphing example now. Let's say we want to graph the function y equals e to the negative x squared over 2. So first let's look at symmetry. If you switch x for negative x, so we've got a negative x squared over 2 and negative of that. Well, the negative x squared is the same as positive x squared. So that's going to give the same equation. So that means we have y-axis symmetry. For intercepts, if you set x equals 0, so plug 0 in here for x, you get e to the negative 0 over 2, which is e to the 0 or 1. So 0, 1 is our x-intercept point. Y-intercept point, because we set x equals 0. And for the x-intercept, if you set y equals 0, so plug y equals 0 in here, set it equal to the e to the negative x squared over 2, that has no solution. So we've got no x-intercept. So 0, 1 and no x-intercept. For asymptotes, vertical asymptotes, there are none because that function is continuous. It doesn't have any zeros in a denominator where it would be undefined. And also, if it's continuous, then it can't have a vertical asymptote. That's continuous everywhere. And then notice that e to the negative x squared is always greater than 0, so it's going to be above the x-axis. For horizontal asymptotes, we look at the limit as x goes to infinity of that e to the negative x squared over 2. So if your x is getting bigger, e to a big negative power, that's going to go to 0. So y equals 0 here is your horizontal asymptote. For increase-decrease, we need a derivative here. So our original function here is e to the negative x squared over 2. That's e to a function. So if you differentiate e to a function, you get e to that function again, e to the negative x squared over 2, and then times the derivative of this inside function. So that's actually the same as this up here is actually the same as e to the negative 1/2 x squared. So 2 can come down times the negative 1/2 will make a negative 1, decrease your power by 1, so negative 1x or negative x. So that's actually going to be negative x e to the negative 1/2 x squared. And then notice since e to the negative x squared over 2 is always greater than 0, remember we want to take this and set it equal to 0. Well, this piece is always greater than 0. So the only way that this product can be equal to 0 is if negative x is equal to 0, which means x equals 0. So x equals 0 is our only cutoff for f prime. So let's look at f prime above the number line and f below the number line. Let's test negative 1 and positive 1. And we'll test those in our derivative here. So if we plug a negative 1 in here for x and square it, we get 1. E to the negative 1/2, that's going to be greater than 0. Plug a negative 1 in for x, negative of negative 1, positive 1. So that'll be positive times positive, which is positive. So our function f is increasing. Plug a 1 in for x here. Well, again, this part's always greater than 0, and then negative 1 out in front. So that's going to be negative times positive, which is negative, and then our function is decreasing. So this is a max point there. That's a relative max. So our function value, so we got a max at 0, and our function value at 0, again, is e to the negative 0 over 2, which is 1. So that 0, 1 is not only the y-intercept point, it's a max point. All right, how about concavity here? So our f prime is right here, and we want to differentiate that to get f double prime. So f double prime is derivative with respect to x of negative x e to the negative x squared over 2. So this is a product of functions, f times g. So we need to do f prime g plus f g prime. So derivative of negative x is negative 1 times your g e to the negative x squared over 2, and then plus f, which is negative x, and then times g prime, derivative of e to the negative x squared over 2. Well, that's right up here. So times negative x e to the negative x squared over 2 again. And so negative x times negative x there is going to be x squared. And then notice we've got that e to the negative x squared over 2, e to the negative x squared over 2. That's a common factor, so I pulled it out in front here. What's left in this term is the x squared there. What's left in this term is a minus 1 there. And then we set that equals 0. And again, this piece is never equal 0, so that means that x squared minus 1 has to equal 0. So bring the 1 over as a positive, x squared's 1, x is going to be plus or minus 1. So those are our cutoffs for f double prime. So above the line we want to do sine of f double prime. Below we want to tell what f is doing. So let's pick some test numbers here. How about negative 2, 0, and 2? So if we plug those in here to our second derivative, this piece is always greater than 0. E to a power is greater than 0. Negative 2 squared is 4, minus 1 is 3. So positive times positive is equal to positive. So f is concave up. Plug a 0 in. So this is positive. 0 squared minus 1 is negative. So positive times negative is negative. Function is concave down. And then plug a 2 in here. 2 squared minus 1 is 3. This is positive. Positive again. Positive times positive is positive, and concave up again. So now let's look up above at the increase decrease, and then we'll adjust what our piece of the graph looks like. So this is concave up. We look up here, f is increasing. So increasing concave up, we're only going to have the right part of that curve. Concave down here, we look up above. If you're to the left of 0, you're still increasing. So increasing concave down is this piece here. So we've got an increasing concave up, increasing concave down. Between 0 and 1, we are concave down. We look up, we're decreasing. So decreasing concave down like that. To the right of 1, we're concave up. We look up above here, we're decreasing. So decreasing concave up. Just going to be the left side of that curve right there. And notice here that our concavity changes here from concave up to concave down. So inflection point here. So inflection at 1. And then concave down to concave up, we've got another inflection point. Inflection at -1 and another at 1. So we need those y values, so f of 1 and f of -1, 1 squared or -1 squared, they both give e to the -1/2 as an exponent, which is about 0.61. So our inflection points are going to be -1, 0.61, and +1, 0.61. So now let's go ahead and sketch our graph. So let's put our two inflection points on there. So we got -1 here, +1 here, that's a 1. So -1, 0.61, about right there. +1, 0.61, about right there. And then we've got our maximum point at 0, 1, which is right there. And so out here we have the x-axis here is a asymptote, right? Because y equals 0, x-axis is horizontal asymptote, so it has to taper off to the x-axis here. But then it has to come up and go through that point. And then it changes to concave down as it's at this point and coming into 1. So something like this, concave down. And then we have y-axis symmetry. So this piece has to, again, go down like that. And then this is now concave up and tapering off to the x-axis. So there's our graph. -1, 0.61, and positive 1.61. And then, of course, you can confirm this on your calculator.